Okay, so welcome back, and now we are going to do the parallel AC circuits. Okay, so last time we did the series AC circuits, and this time we are going to do parallel ones. I won't bother you with like revisiting this one for series and parallel circuits because you can watch the previous video if you want to know more about it, and you should watch how to do AC circuits before you know how to do parallel AC circuits. But anyway, let's start. So we'll start again like last time with some simple and basic stuff, such as finding the total resistance in this parallel circuit. We know that the resistor is got 50 ohms and the inductor got a value of 25 ohms. So how do we calculate this? Well, it's simply we calculate it like we calculate a normal two parallel resistors. We simply do 1 over ZT is equal with 1 over ZR plus 1 over ZL, and we can also rewrite this one as 1 over ZT is equal with 1 over 50 plus 1 over 25, which that one would be equal with 1 over, no, that one would be 0 0.02, so 0 0.02 at an angle of 0 degrees plus 0 0.04 at an angle of minus 90 degrees. Okay, so why is that? Well, we've used the z values, so in the z values we also need to put the degrees. That's a plus and that's a plus. Sorry, because in the no, it actually it's a minus. Yes, it's minus, and this one it's a plus here. It reverses the sign each time you do 1 over that number, because this one's got an angle of 0 degrees. When you do like 90 minus 0, that'll give you, no, 0 minus 90, that'll give you minus 90. So that's why the sign reverses here but not here. Okay, so let's keep going. So then ZT will simply be equal with 1 over 0 0.02 at an angle of 0 degrees, because that's the resistance, plus 0 0.04 at an angle of 90 degrees. But the problem, because that is the inductor. However, the problem here is that we need to add them together. We can't just use it like this. And when you add them together, we can calculate it if you wish to. We can say that the x value for r will be equal with 0 0.02 cosine of 0 degrees, and that recipe gives 0 0.02, while y is equal to 0 0.02 at a sine of 0 degrees, and that will give us 0. And then x for the inductor value will be equal with 0 0.04 times cosine minus 90 degrees, which is equal to 0, and y is equal with 0 0.04 times sine at minus 90 degrees, and that one will be equal to minus 0 0.04. So this one will simply be equal with 0 0.02 plus 0 plus j0, while this one will be 0 plus minus j 0.04. Remember the minus and plus sign, this is very important. So when you combine them together, you get 0 0.02 minus j 0.04. And to know the total value ZT, we'll simply do 1 over this value here, and then that one will be equal with, so wait a second. Okay, so we can't really do it yet because this will change the angle if you do it now, and we need to maintain the same angle. So therefore z is equal with square root 0 0.02 squared minus, there you go, 0 0.04 squared. That one becomes a plus because it's b squared anyway, and then that one is equal to 0 0.045. The angle is equal with tan minus 1 of minus 0 0.04 over 0 0.02, and that will be equal to minus 63.43. And there we have it. Now we made it into polar form, so ZT will be equal with 1 over 0 0.04 63.45 at an angle of minus 63.43 there, and that will be equal with 22.2 at an angle of minus 63.43 degrees, because the angle doesn't change, only the real number changes, and 1 over 0.04 will be equal with 22.2. And there you have it. That's how you calculate the total resistance in a parallel circuit. And you can already see that's a bit more complicated than the previous example, which was in series circuits, where we simply added them together. It's a bit more complicated because they're calculated in parallel, but don't worry, this will get easier and easier, because in the next example we'll have RLC, which this will be a bit more complicated than the previous one, but not by much. Again, let me put this a bit higher. I did a mistake here. I thought there was current and voltage source, but there is none, so that's why I cross it out. So ZT will be equal with 1 over ZR plus 1 over ZL plus 1 over ZC. Basically these three values: resistor, inductor, and capacitor. So we can also rewrite this one as 1 over 110 at an angle of 0 degrees because the resistor, plus 1 at 16 because there's the resistance inside the inductor at an angle of 90 degrees because it's an inductor, plus 1 at 40 because that's the resistance inside the capacitor, 40 ohms, at an angle of minus 90 degrees. Alright, and now we can calculate it. First we'll do it the first stage, which will be dividing them. So then CT will be equal with 1 over 0.1 at an angle of 0 degrees plus 0.0625 at an angle of minus 90 degrees. Remember, 1 over 90 degrees, it will just reverse the sign to a minus sign, plus 0.025 at an angle of 90 degrees. And there we have it. Now we can simplify this one even further, because as you know, minus 90 degrees and 90 degrees, they can be replaced in J values. So when we replace in the J value, we can say that this one will be equal with 1 over, let's see, it will be 0.1 minus J 0.0625 plus J 0.025. Alright, and then this one will be simply equal with 1 over 0.1 minus J 0.06. Alright, so this is the value that we are working with, and the last step is simple, and that is to replace this, to convert these values to a polar form, and then perform the last equation. Remember, perform the first transform in polar form and then perform the last equation. If you perform the last equation now, then it will change the value of J, and that one will kind of ruin the answer. That's why we do it right before the last equation. So Z will be equal with square root 0.1 squared plus 0.06 squared, and that will be equal to 0.117. Now we can calculate the angle. So angle will be tan minus 1, the y value, which is 0.06, it's a minus, of put minus here, and then under will be 0.1, and that one will be equal with minus 30.96 degrees. Alright, and now we can solve the problem. We can go to the last step of saying ZT is equal with 1 over 0.117, angle of minus 30.96 degrees, and that one will be equal with 8.55, so the angle doesn't change, it will be minus 30.96 degrees. Well, actually the angle does change, it will become a plus, and I think I think the same mistake on this one here as well. This is supposed to be plus as well. In the last step the angle does reverse, so they'll become plus, positive angles instead. Sorry about that, I just noticed that as well now. Alright, so now that the angle is positive, well, I guess we are going to go to the next examples. This one should sum up how you calculate the total resistance with the total angle as well. So the next example would be this one here, which is a little bit more complicated. Basically, it's a voltage source that has a positive 60 degrees to it, and then we need to find out the current through R1 and the current through R2. All right, and we have here a resistor and an inductor. All right, how do we do this? Well, first things first is we convert the source into the values that we know into RMS values. Is my camera straight? Yeah, it is straight. Okay. I'll check quickly the camera to see if it's alright. In the camera, yeah, it's alright. Everything. Okay. So first we convert the source to RMS, so that'll be 25 times 0.707. That one will be equal with 17.675 at an angle of 60 degrees, because this is a plus 60 degrees as well. Alright, now we need to calculate the total resistance with the total angle, so we can determine the current, the total current. Alright, so then ZT will be equal with 1 over 10 to the angle of 0 degrees. Again, I'm using this formula because it's the one that I like to use. ZT is equal with 1 over ZR plus 1 over ZL plus 1 over ZC. This tree can be any components you want or anything you want. I like to write it like this because it's more self-explanatory, you know. If I put Z1, Z plus Z2 plus Z3, that doesn't really mean anything. That just means like a random component. While if I put this one, I can show you that yes, you can use resistors, inductors and capacitors. Alright, plus 1 over 5 at an angle of 90 degrees. This will be equal with 1 over 0.1 at the angle of 0 degrees plus 0.2 at an angle of minus 90 degrees. Right, and this one will be equal with 1 over 0.1 minus j 0.2. And again, you can like use the y values instead of the z values to calculate, like if you want to know, if you want to do it this way. But again, I find more useful to do it into the z format. And don't worry, like parallel circuits aren't very different from series AC circuits, because simply put it, they are the same thing. They use the same formulas and the same concepts. The only difference is how you calculate the total resistance with the total angle, and also how you determine also that the components across it have the same voltage. That's why I'm asking for the current in here. It doesn't really make that much sense to ask for the voltage because all three of them uses the same voltage. Alright, so then we convert this one to polar form. So z is equal to square root 0.1 squared plus 0.2 squared, that is equal to 0.224. Then the angle is equal to 10 minus 1, 0.2 over 0.1 with a minus in here, that will be equal to minus 63.43. Alright, now we do 1 over 0.224 angle of minus 63.43, and then the sign reverse, that will be 4.46 at an angle of 63.43, and this is the value for ZT. Alright, so we know the total resistance is the total angle. Now we can simply calculate the total current by doing I is equal with E divided by ZT, which is equal with 17.675 at an angle of 60 degrees divided by 4.46 at an angle of 63.43 degrees. Okay, and then the answer will be 3.96 amps at an angle of minus 3.43 degrees. So this is our answer. This is our total current, and now we can calculate it separately for each component. And what do I mean by that? Well, the ground is here. I choose to put the ground in here. So because the current goes like that through here and through here, and they use the same voltage, I can just simply apply the current formula and replace the total resistance with simply the resistance inside the resistor or inside the inductor, and I'll show it to you in a second. Okay, so the way that I can do it, it's simply write it as IR is equal with the total source, because there's only one source and all components are in parallel, so there is no difference, there is no need for renewed analysis or anything like that. So that's E, and then ZR, and now we can replace the values. So there'll be 17.675, an angle of 60 degrees, over, that will be 10 ZR at an angle of 0 degrees. And sorry, my laptop just closed and I was like, never mind, I'll leave it in sleep mode. I was like editing one of my videos and I was waiting for it to render. By me. Okay, that will be 1.77, an angle of 60 degrees, because that doesn't really change, because 60 minus 0 is still 60. Okay, and this one is the current IR, and I can also like check it later actually, so I'll do so. I'll say that x is equal with 1.77 cosine of 60 degrees, that's equal to 0.885, and then y is equal with 1.77 sine of 60 degrees, and that's equal to 1.533. 0.885 plus j 1.533. So this is the rectangular form of the current, and you'll see in a second why I want to have the rectangular form as well. And now we calculate it for the inductor, so IL will be equal with never mind, I got a message that doesn't really matter. IL will be equal with E over ZL, and that will be equal with 17.675 at an angle of 60 degrees divided by it's got a resistance of 5, so CL is 5 at an angle of 90 degrees because it's an inductor. And then that is equal to 3.535, then angle of minus 30 degrees. Okay, now let's calculate the x and y values. So the x value is 3.535 cosine of minus 30 degrees, that's equal with 3.06. Now y is equal with 3.535 at the sine of minus 30 degrees, and then that one will be equal with minus 1.77. Together they will give me 3.06 minus j 1.77. Alright, now let's calculate the total current to see if our answer is correct. So because there's one current here, the total current is here, then the total current should be equal with IR plus IL, because if you pick this node here, one current is coming in and two currents are coming out. Okay, so then the total I is equal with IR plus IL. Okay, so the way we do this is by doing this one. So we did it in rectangular form. When it's in rectangular form, we can easily add them together to be 0.885 plus j 1.533, and there we close the bracket, plus, then we open a new one, 3.06 minus j 1.77, then this will be equal with 3.945 minus j 0.237. Alright, now all we need to do is to change this one in polar form, and once we change it to polar form, we can see if it's the correct answer or the wrong answer. So let's change it to polar form. Z will be equal with square root 3.945 squared plus 0.237 squared, then that one will be equal with 3.95. Okay, now we calculate the angle, which is equal to tan minus 1 minus 0.237 over 3.945. Then this one will be equal with minus 3.437. Okay, so together it will give me 3.95 at an angle of minus 3.437 degrees. And is it the right answer? Yes, you could say. I mean, I would say it's kind of like close enough. 3.957 and 3.96, and then minus 3.437, and this side it's minus 3.43, and then there is nothing else after it. I would say it's close enough, to be honest. I mean, like, you won't get a perfect number, but it's better than like not getting the correct number, isn't it? Anyway, let's keep going. So now we need to calculate the total power, and likely the formula for the total power is still the same. It's just the total voltage multiplied by total current multiplied by the cosine of the t. So E times I times cos cat t, that time will be equal to 17.675 multiplied by 3.96 multiplied by cos 63.43, and that will be equal to 31.3 watts. And that's the power, which is quite low, but it's fine. It's only two components in parallel, and also the current to them is very small as well. But anyway, okay, so this is done. Let's go to the next one, which is, I think is this one, isn't it? Yeah, I think it's this one, because it's using a current instead of a voltage source. Yeah, okay. So now we are going to have a capacitor instead of an inductor, and a current source instead of a voltage source, and we need to find the E value, which will be like convert this current source to a voltage source, the IR and IC. All right. So actually, for the previous one, it's not on this page, it's on this one. If you wish to like do it properly, like if you want to know the peak current values, well, then you can simply do like I will be equal with 3.96 multiplied by square root 2, and that will be equal with 3.96 multiplied by square root 2. That'll be 5.6, so 5.6 sine WT minus 3.43 degrees. And we can do so for the other ones. So for IR would be equal with 1.77 times square root 2. That's equal with, so 1.77 times square root 2. That's 2.5 sine WT plus 60 degrees. Now for the last one, which is IL, will be equal with 3.535 times square root 2. That's equal with, so 3.535 times square root 2. Yeah, let's say it will be 5 sine WT minus 30 degrees. Okay, and these are our answers in like the peak value forms, in case that you want them to be like peak values. If you don't want them to be peak values, just leave them RMS values. Don't worry about it. Unless it specifically says that they want the peak values, then I guess leaving them RMS values is fine. Alright. So now let's go to this one here. Oops. Let's go to this one here. And let's keep going. Alright. First of all, like usual, we need to convert this one to an RMS value. So it will be 14.14 times 0.707. That will be equal with 10 amps at an angle of 30 degrees. Alright, so that's our current I. Now we need to calculate the total resistance with an angle, so ZT will be equal with 1 over ZR plus 1 over ZC. That one will be equal with 1 over, and the resistor got 3 ohms, so it will be 3 ohms at an angle of 0 degrees plus and then the capacitor is got 1.5 ohms, so it would be 1 over 1.5 at an angle of minus 90 degrees, because remember it's a capacitor, so it's got a negative value for now. When we do it, like when you calculate the 1 over the value 1 over 3 and 1 over 1.5 angle of 90 degrees, then the new values that we'll get will be 1 over 0.33 at an angle of 0 degrees plus 0.667 at an angle of 90 degrees. Alright, and we can also rewrite it as 1 over 0.33 plus J 0.667. And before we do it again to find the total resistance with an angle, we'll need to change this sign into a polar form. So Z will be equal with square root 0.33 squared plus 0.667 squared. And that one will be equal with 0.744. And now we can calculate the angle, which will be equal with tan the minus 1, 0.667 divided by 0.33. That one will be equal with 63.47 degrees. Alright, and let me check actually. So are there any negative values in here? No, there are only positive values. It's okay then. Okay, so then ZT will be equal with 1 over 0.744 at an angle of 63.47 degrees. So this one will simply be equal to 1.34 at an angle of minus 63.47 degrees. Let me check if that's the correct answer. 1 over 0.744. Yeah, it is 1.34. Okay. Alright, so now we find the total resistance and the angle of that total resistance. Now we can simply find the E value. So then E will be equal to I, the current multiplied by total resistance ZT, and then that one will be equal with then the angle of 30 degrees, which is the current that we determined here, multiplied by, and the total ZT is 1.34 at an angle of minus 63.47 degrees. And you can see that the current will be equal with 13.4 at an angle of minus 33.47 degrees. Alright, now that we find the voltage E, now we can easily find the current. Why? Well, because E is in parallel with R and also it's parallel with the capacitor. All three of them will have the same voltage. So we can easily calculate the current by just doing voltage divided by resistance. Alright, so then let's see here. So IR will be equal with E over ZR, and that one is equal to 13.4 at an angle of minus 33.47 over 3 at an angle of 0 degrees. And in that one it's equal with 4.46 at an angle of minus 33.47. And that is a value that we need to remember, so let's square it up. And if you want to know like what the current is, we can also multiply by square root of 2, and that will give us 6.3 sine WT minus 33.47 degrees. Alright, now let's go for the next one, which is IL, which will be equal with 13.4 at an angle of minus 33.47 divided by 1.5 at an angle of minus 90 degrees. And then this one will be equal with 8.93 at an angle of 56.53. Then we'll multiply by 2, the square root of 2, then we go with 12.63 sine WT plus 56.53 degrees. There we go. So now we found out the capital value, like the RMS value, which is this one here that we boxed right now. And these two are the normal values that are used like every time. All right. Those are the peak values, not really, you can't really call a value normal, these are the peak values. Now let's keep going then. So then IT is equal with 3.72 minus J 2.46 plus 4.92 plus J 7.8. Oh my god, I'm sorry. I forgot to convert them. Sorry about that. So IR, the x value is equal with 4.46 times cosine of minus 33.47, which is equal with 3.72. Y is equal with 4.46 times sine minus 33.47, and that is equal with minus 2.46. When combining them together, we get 3.72 minus J 2.46. Now IL, the x value will be equal with 8.93 times cosine 56.53, which is equal with 4.92, and then y is equal with 8.93 times sine 56.53, which is equal with 7.45. Together there will be 4.92 plus J 7.45. Okay, and now I can add them together to find the total current IT, which will be equal with 3.72 minus J 2.46 plus 4.92 plus J 7.45. Then that will be equal with 8.64 plus J 4.99. Alright, so now we can convert it into polar form. So Z is equal to square root 8.64 squared plus 5 squared. Instead of 4.99, they just put 5 squared. That one is equal with 9.98, or we can just write it as 10 amps. And then the angle is equal to 10 minus 1, 5 over 8.64. That is equal to 30.06, or we can also write it as 30 degrees. So therefore IT is equal with 10 angle 30 degrees. Therefore, so all the values are correct. So the IR and IC values, and therefore the E value, because we use the E values, are correct as well. Why? Well, we get our total current, which is 10 amps at an angle of 30 degrees. We got this value right here when we did the calculation and checked all the workouts. All right. And I guess now we can just convert it back. So actually there's no point in converting the I total back, because it will be just the same number as the source, which is 14 sine WT plus 30 degrees. So let's do it for the E. So E will be equal with 13.4, an angle of minus 33.47 degrees, and we just multiply by square root of 2. That one will be equal with 18.95 volts sine WT minus 33.47 degrees. And this one is the calculation and the answer for a parallel AC circuit with a capacitor. As I said during the complex number lesson and the AC series lesson, these problems will get longer and longer solutions. The reason why this solution is longer, at least by a few steps, is because of this one here, you know, us check, actually it's all the way here, just us checking to see if the current and the calculations are correct. You may say like this part here is useless, you know, we don't really need it, but the thing is that we do kind of need it, you know. There you go, now you can see it, this section here. We do kind of need it because we want to like see if the values match the total IT and to make sure we didn't do any calculations wrong. Okay, first thing I got scared. I thought that my camera stopped. I really don't want to like record myself for like another hour because the camera stopped. Alright. Now, as you probably expected, we are going to use three components now. We're going to do it the resistor, we're going to do it the inductor, and we are going to do it the capacitor as well. And again, we are going to use a voltage source, but this time it's different because we got a frequency of 60 Hertz and we also got plus 80 degrees in here. And we need to find the current, we need to find ZT and I and the value and power. So I won't bother you to find in like each individual current. If you wish, you can do that. But what we need to do is to find the ZT value and the current value and the power value. Why I do so? Because as you see, we're using 5 ohms for the resistor, but it's like 10 millihenries for the inductor and 150 microfarads for the capacitor. And the reason I use these low numbers, it's because, you know, to make it a bit more complicated and also to get the chance to use a frequency of 60 Hertz. And if I were to calculate for each one of these sections the current, then it will be a lot longer of a solution. Alright, so this page is done. So I'm going to go to the next one. And oh, I see that we already like calculated for each one of them. Actually, it's not that much of a hassle. So let's do it actually. So let's calculate for like IR, IL, and IC. Let's just add a little bit extra. If you are doing it, let's do the whole thing then. Plus, there's not much left. We are already like halfway through. There are 3 more exercises left. So it's okay. But this video will still be a 2-part video because I did minute 40. Alright. So first things first. What do we do? Well, we can I'll say that first we need to find the angular velocity. I think that's the very important first step that we need to do. So W is equal to 2 pi multiplied by the frequency, which is equal to 2 pi multiplied by 60 Hertz. And the answer for that one will be 377 because we did it before with the series AC. There'll be 100 sine, no, that'll be 377. Okay, so then E it's equal with 100 sine 377 t plus 80 degrees. Next step will be to find the XL value, because we can't use henries, we need to change it to ohms to use the resistance. So XL will be equal with, this got the value of 10 milli, so 10 times 10 to the minus 3 multiplied by 377, and that will be equal with 3.77. Is it like milli or is it not? Let me check. So 10 times 10 to the minus 3 times 377. Yeah, it's just 3.77. Okay, ohms. Now we need to find the same one, the resistance for the capacitor. That will be 1 over WC. So that will be 1 over 377 times 150 the power of 10 minus 6. That one will be equal with 17.69 ohms. Okay, and there it's our answer converted. Actually, let me convert this one also to the, how is it called, the RMS value. So we'll do capital E, it's equal with 100 times 7.07, no, 0.707, then that one will be equal with 70.7 at an angle of 80 degrees. All right, now let's redraw the diagram so it's easier for us. So when we redraw it, we put the AC source in here, one resistor in parallel, one inductor, and one capacitor. This one will be R, 5 ohms. This one will be XL, 3.77. This one will be XC. This will be 17.69. Okay, and here at the source, E will be equal with 70.7 at an angle of 80 degrees. All right, so that was the first step. The next step actually is a little bit more creative. I was thinking about calculating the total ZT and then calculate the total current, but let's do it a bit different this time. Let's calculate each IR value separately, and then we calculate the total current, and then we use the total current to calculate the total resistance, which will be ZT. So let's do it backwards, instead of doing it the way that we did it before. Shake things a little bit. So then IR will be equal with E over ZR. That one will be equal to 70.7 at the angle of 80 degrees divided by 5 at an angle of 0 degrees. That one will be equal to 14.14 at an angle of 80 degrees. IL would be equal with E over ZL, that will be equal to 70.7 at an angle of 80 degrees over 3.77 at an angle of 90 degrees. And that one will be equal to 18.75 at an angle of minus 10 degrees. And now IC is equal with E ZC ZC is equal to 70.7 at an angle of 80 degrees over 17.69 at an angle of minus 90 degrees. And that one will be equal to 4 at an angle of 170 degrees. Alright, now the next step will be to convert these ones in a rectangular form so we can add them together and find the total current. So then IR will be d dots x is equal to 14.14 cos of 80 degrees. That one is equal to 2.46, and y is equal to 14.14 sine 80 degrees, and that one is equal to 13.93. So the answer here will be 2.46 plus j 13.93. Now we do the next one, which will be IL. The x value will be equal with 18.75 cos let's see here, so 18.75 cos minus 10 degrees is equal with 18.47, and then y will be equal with 18.75 sine minus 10 degrees, and that one will be equal to minus 3.26. Together they will be 18.47 minus j 3.26. Now we do the IC. So IC will be 2 dots x is equal with 4 cosine 170, which is equal to minus 3.94, and then y is equal with 4 sine 170, and that one will be equal to 0.69. So then the answer for this one will be minus 3.94 plus j 0.69. Alright, now to find the total current in rectangular form, we just need to add all three of them together. So IR plus IL plus IC will be equal with 2.46 plus j 13.93 plus 18.47 minus j 3.26 plus minus 3.94 plus j 0.69. Alright, and then this one will be equal to 17 plus j 11.36. There we have it. Okay, that's the total current, but this one it's in rectangular form. We need to make it in polar form so we can actually know what the values are. So then z is equal to square root 17 squared plus 11.36 squared, which is equal with 20.45. Then the angle is equal to 10 minus 1, 11.36 divided by 17. That one is equal to 33.75. degrees. Alright, so then IT will be equal with those two values, so 20.45 amps at an angle of 33.75, which is kind of impressive. It is kind of a lot of a current, but also the voltage is quite high as well. It's about 70.7, so I guess 20 amps kind of fits in. Don't worry, we're going to check this one as we go on through the problem, because the problem is not done yet. We did find the I value, but we still need to find the total resistance, and we also find the little i's. No, and we also find the current through R, the current through L, the current through C. Actually, let's find the little i's as well. So that will be that value multiplied by square root 2. That will be equal with, what's that? It's like 20, isn't it? 14.14 times square root 2. Yeah, that's 20 at an angle of 80 degrees. No, let's write it properly. That'll be 20 sine W, that's 377 T plus 80 degrees. Okay, we multiply this one by square root 2. That will give us, so 18.75 times square root 2. That's 26.52. So 26.52 sine 377 T minus 10 degrees. Right, next one will be square root 2, which that will be equal with, so 4 times square root 2, that will be 5.66 sine 377 T plus 170. There you go. So now we also know the little IR and little IL and little IC values, because we simply multiplied the RMS values, we converted them back to their peak values. Okay, so I don't have space in this anymore. I guess I'll have to take a new page. Okay, so there's a new page, and there is the old one with the exercise on it. Alright, so now that we find them, we just need to find ZT. So the way that we find ZT, let's use the total current and the total voltage. So then ZT will be equal with, it will be E over IT. There you go. And that one will be equal with, so E, that's 70.7, an angle of 80 degrees, divided by IT, which is 20.45, an angle of 30.75. Wait a second, I need to calculate this one, because on my notes I did the other way around, you know, I did the simple way to calculate it. And then now let's see, like, if you get the same answer as the notes. So 0. So fraction 70.7 divided by 20.45, 70.7 divided by 20.45, there'll be 3.56 let's say, and then the angle will be simply 80 minus 33.75, that one will be 46.25. Okay, and I guess they are similar. Here in my notes I did a calculation as well, as you see. I'll just like highlight it for you, so it's in this square here. So as you see, I did ZT 1 over I0R1, 1 over that, and then I do 1 over 5 the angle of 0, 377 the angle of 90, 1 over 70.69 the angle of minus 90. So I did all the calculation here. I converted from this form, from this rectangular form to polar form, and the answer that I got here is 3.45 at the angle of 46.4, and the answer that I got here is 3.46 at an angle of 46.25. Again, I think they are close enough. It's not really perfect, because this one I used two made up values. I used the value of E and I used the value of I, and they're not the most precise values, you know, it's not like to the last decimal point. while this one here, I guess it's a bit more accurate. But the two values are very close to each other, so I'll consider them correct, to be honest. All right. So like, because we did it differently here. But anyway, so let's say this one is correct. Okay. There you go. So now we can easily calculate the power. So then PT will be equal with E times I times cos of the angle total, and that one will be equal with, oh yeah, and for the current, actually if I had this paper I might as well check both of them. So for the current, which is this one here, I got 20.45 at an angle of 33.6, and we got here for the total current, we got, look at that, we got the same thing, almost the same thing. We still got, let me, there you go, yep, and this one here, like that, there you go. So we still got 20.45 angle of 33.75, but here we got like an angle of 33.6. Again, very close to each other, and I'll consider it correct. It's because I used a different method, and use a different method, the answer might be slightly different. Anyway, let's keep going. So E times I times cos of t, so that'll be 70.7 multiplied by 20.45 times cosine of 46.25. So this one will be equal with, it should be 997 watts. There we go. So this is it actually? Let me check, because we have used a different angle, don't we? Times 20.45 times cosine 46.25. Yeah, it's a bit different. It's like 99.8. So I'll just put like 1000 watts. There you go. Which this one seems a bit more correct, to be honest. I mean, like, I see it as more correct because it's a whole number. Anyway, so yeah, we determined the power and we determined the total resistance with the total angle as well. Okay, so that was it for this one here. Again, if you get it off by a little bit, if you do it in two methods, don't worry, like the answer is still correct. Because like if it's only like 0.1 or 0.2 difference from like 50 or 60, that's not a big difference. If it was a difference of, let's say, 5 or 10, then yeah, that would be a big difference. Anyway, I'll stop the recording here because it's already been almost an hour, and we'll need to go to the next exercises because we got 3 more to do. Okay, hopefully you understand the way that I solved this one here, because no, not this one here, this one here, because quite important. Like in AC series circuits, we can also simplify multiple components into just 3 parallel components. But remember, for the AC and for the parallel, I can do that because it's only one source, and all of them were either parallel or all of them were either series. In the future, where we'll get to the more complicated stuff, like after the series parallel circuits that have both series and parallel, after that one we are going to do network theory for AC circuits. And what do we do in network theory for AC circuits? Well, basically we learn how to calculate it when there are 2 sources, and when there are 2 sources, you won't always be able to simplify a circuit to just 3 components, you know. And I'm not very familiar with that, like most of the stuff that I'm doing now. That's why the videos took a bit longer to come out as well, is because I'm learning at the same time as y'all learning. First, I'm learning for myself to understand how to do this and to come up with a few problems in which I see like complicated or important to understand. And after that, after learning for myself, I do the problems and I'll try to teach you how to do the problems as well. But anyway, thank you for watching. This is the first part of the parallel AC circuits. So I'll see you in part 2.